This video will explain how to solve problems related to soil constituents, and we'll start with the problem number 1, when there was a field density measurements and we obtained a soil with the mass of 8,880 grams. The volume of this soil was 900 cubic centimeters. And when the soil was dry, the mass of dry soil became 1,640 grams. And the specific gravity of this soil solids is given to us. It's 2.69. We're going to use these measurements to calculate the water content first. Then we will determine the dry density of the soil, void ratio. I'll also look at the degree of saturation, and in the end we'll find the volume of air and air content. Let's start with the water content. So remember that water content is the ratio between mass of water divided by mass of solids. So in this case, mass of dry soil will give us actually mass of solids, because there is no water in the soil, and if there is air, but air has no mass. So what we're going to do next, we will find the mass of water. We're going to look at the difference between the total mass and the mass of dry soil, and that will provide us with mass of water. It's 8,880 minus 1,640 give us 240 grams. So now we'll find the water content. It's mass of water, which is 240 grams, divided by the mass of solids, which is also mass of dry soil. And this ratio will be about 0.146, or if we change it to percentage, it will give us about 14.6% water content. Now let's look at the dry density. Dry density, it's the mass of solids or mass of dry soil divided by the total volume of the soil. We already know the mass of solids. It's 1,640 divided by the volume 900 will give us approximately 1.82, and we're going to use grams per cubic centimeters. Okay, that was easy. Next one is a little bit tricky. The way we're going to do the void ratio is we need to use the definition, which is the ratio between volume of voids to the volume of solids. What we'll do first, we will find the volume of solids, then we will find the volume of voids, and then we will find the void ratio. We'll start with the volume of solids. From the definition of the density of solids, it's going to be mass of solids divided by the density of solids. When we talk about density of solids, we should most likely use specific gravity, because specific gravity has density of solids in its definition, as shown here, and then it will lead to the formula as density of solids, it's equal specific gravity times density of water, and this will take us to volume of solids equal mass of solids divided by specific gravity and density of water. So we know the density of water is equal to 1, We know that mass of solids is equal to 1640 and the specific gravity is 2.69. If we put all the numbers in the formula, we're gonna get that the volume of solids is approximately 609.7 cubic centimeters. Now we're going to use the definition of volume of voids. It's total volume minus of volume of solids. So you will see that volume of voids here, it's the total volume minus this volume of solids. In this case, we can get that volume of water will be, volume of voids will be 900 minus 609.7, which give us approximately 290.3 cubic centimeters. And now we just put it in the formula. Volume of voids, it's 290.3 divided by 609.7 will give us approximately 0.476. Remember, for the void ratio, we don't use percentage, we just use the ratio. Next problem is degree of saturation. So degree of saturation, we use capital S, and it's volume of water divided by volume of voids. In this case, we'll just find first the volume of water. Again, we're going to use the definition of density. It's mass of water divided by density of water. We know the mass of water because we measured it and we already obtained it in the first question. It will be 240. And the density of water is assumed to be 1. That will give us the volume of water 240 cubic centimeters. And then we're just going to find the degree of saturation, which is from the formula 240 divided by 290.3 will be approximately 0.827, or if we change it to percentage, it's going to be 82.7%. So this means that about 82.7% of the voids are filled with water. And the last bit is the volume of air. The volume of air can be obtained from the definition of volume of voids, which is volume of voids minus volume of water. And we already know the volume of voids, it's 290.3. Volume of water, also we already obtained this, it's 240, which give us approximately 50.3 cubic centimeters. And air content, it's volume of air divided by total volume, and we can put it in percentage. That will be about 50.3 divided by 900 times 100% will give us approximately 5.6%. So this means that this soil has a little bit of air in it. It's about 5.6%. For the second problem, we will use a different approach. We're not going to use the definitions anymore. We'll just use formulas, and this will make it a little bit easier and faster. So let's look at the problem. There was embankment built, and the soil was compacted to density of 2.15 megagrams per cubic meters, and we also know the water content, which is 12%. The value of specific gravity is given as well, it's 2.65. So let's look how we can calculate the dry density, unit weight, void ratio, porosity, and degree of saturation. We'll start with dry density, and we need to remember that dry density it's the ratio between the density of soil divided by 1 plus water content. So in this case, we are given bulk density, which is the same thing as a density, or the same thing as moist density, and that's the value that we're going to use, 2.15 divided by, and we're also given the water content. The water content is given in percentage. We need to change it to the ratio, 0.12, and that will give us approximately 1.92 megagrams per cubic meters. So this is the dry density of this compacted soil. Now let's look at the unit weight. The definition of unit weight is density of soil times the gravitational acceleration, and the density of soil we already know it's 2.15, and we're going to multiply by 9.81, which will give us approximately 21.1 kilonewton per cubic meters. Make sure that your results make sense. The unit weight should be in the range from 15 to 2021, depends on the density of soil. So in this case, we'll see that the unit weight is at the high range, which means that the soil was compacted to a high level and it's really dense. And also remember that the unit weight has different units from density. It's kilonewton per cubic meters. Well, to get the void ratio, I think we'll need to use a few formulas. And the one that we can use in this case, it's this one, unit weight. It's specific gravity times 1 plus water content divided by 1 plus void ratio and times of unit weight of water. I wrote it for unit weights, but we can still do the same thing for density. So we can replace unit weight with densities. And in this case, we know that unit weight is 21.1. So we'll just change it to the density, and density of this soil will be 2.15. Actually, it's already given to us, megagrams per cubic meters. And density of water, we assume it's equal to 1 megagrams per cubic meters. So what we're going to do now is we're going to use that equation, just modify it a bit. 1 plus void ratio, it's equal 2.65 times 1 plus water content. Remember to use ratio for water content, and times 1 divided 1 is the density of water divided by 2.15. So 2.65 is the specific gravity. Cheers. Then we get that 1 plus void ratio, it's approximately 1.38. which will give us that void ratio. It's approximately 0.38. This is actually a very low value for void ratio, which means that the soil is really dense. Well, you will see that high values of unit weight correlate with low values of void ratio. Okay, next will be porosity. We'll look at porosity as a ratio, as a relationship between void ratio and porosity. That we already know. And then we're just gonna rewrite it as porosity is equal void ratio divided by 1 plus void ratio, and that will be about 0.275, or we can change it to percentage, 27.5%. Remember that we don't use percentage for void ratio, but we can use percentage for porosity. For degree of saturation, there is a very good formula. It's given as this one. It's water content times specific gravity and divided by void ratio. This is very good formula because it relates all important parameters as specific gravity, void ratio, water content, and degree of saturation. So we're just gonna put all the numbers that we already know. It's 0.12 times specific gravity is 2.65 divided by the void ratio 0.38. That will give us approximately 0.837. We can change it to percentage. It's going to be 83.7%, which is the degree of saturation. Problem 3 is related to relative density. It's not actual density, the way that we use it for soil in grams per cubic centimeters. Relative density shows you how loose the soil is. So we use relative density to classify sand material or gravel. Based on the number of relative density, we can see if the soil is very loose, medium, dense, or very dense. Of course, for most of engineering applications, we would like the soil to be in the dense or very dense range. In nature, it can be from very loose to medium. So what we will need to do is we will need to densify the soil. So we can either do compaction, or if necessary for soft material, we can do consolidation. Let's see how we can use relative density, and we can actually apply it to solve some real-life problems related to liquefaction. So we have a soil sample, and we examined the soil sample, and we got the maximum and minimum void ratios. So maximum is 0.751, and the minimum void ratio of the same soil can be 0.412. So we would like to see if the soil is in its loose state or dense state, and based on the relative density we can decide if the soil can be susceptible to liquefaction during, let's say, earthquakes or very rapid loading. So what we need to do is we're going to use the value of density from problem number 1, and we already found in problem number 1 that the void ratio is equal to 0.476, and we know that the maximum void ratio that we can get from this soil it's 0.751 when it's in its loose state, and when it's in its dense state we can get the minimum void ratio, which is 0.412. So apparently this soil has a void ratio which is in the range between maximum and minimum values of void ratio. So we'll see if it's closer to its maximum value or its minimum value. We're going to use equation for the relative density, which is maximum void ratio minus void ratio of soil in situ in the field divided by maximum void ratio minus minimum void ratio. So we're going to use the numbers we already know, 0.751 minus 0.476 divided by 0.751 minus 0.412. That will give us approximately 0.81. We can change it to percentage by multiple hundreds, and that was about 81%. So that we'll see that 81 falls in the range of dense. So this means that the soil in its natural state, when it's in the field, it's in a dense state, which is very good. If sand is dense, so it's not going to be susceptible to liquefaction. So I'm going to write here dense sand, and if I answer the question of the problem, it says it's not susceptible to liquefaction. Not susceptible. So in many countries like Japan, China, US, New Zealand, many types of soil, they're in a loose or very loose state. So when there is a strong earthquake, they will liquefy. But if we manage to make it denser, so in this case, that soil is not going to liquefy. So from this example, we see that if soil is in its dense state, what we have it from problem 1 and problem 3, and this means that there is no liquefaction for this soil.